Thank you, and thanks to Hartmut Kramer for inviting me to, and Loicz, to provide this heritage lecture. This is being filmed, so I have to behave myself. And they say that it's for many generations, people will look at this, and I think they ask people to give this who are close to the end of their careers. So this is very sad news for me. Anyways, I'd like to thank the list of symbols that you see there. These are the sponsoring agencies that are behind this talk. Loicz, the Global Water System Project, and the Community Surface Dynamic Modeling System. Together, we funded and organized a workshop that led to this talk, to a number of papers in atomic science, nature geoscience, and a few others. And this presentation has a list of many authors. You can read about them in those papers. And I also would like to acknowledge the people that provide the principal funding for my work, the National Science Foundation, NASA, and University of Colorado. So the talk is Deltas Under Climate Change, the Challenges of Adaptation. The outline, I'm going to tell you a little bit about the human footprint on deltas in terms of threats and consequences. And I will say a few words on strategies for adaptation. And I've broken that out from my own perspective in terms of improved understanding. We need much more knowledge. We need better observing systems. And we need better governance. And the nice picture here is topography on a delta, in this case the yellow delta. Areas in pink are below sea level, which is not a good thing. So this leads us to this picture and how people can adapt to living on deltas. It so happens that there are about 500 million people who live on deltas. And so the definition of adaptation is it's an evolutionary process whereby a population becomes better suited to its habitat. And it's important for an organism's survival. And in this case, we're the organism. And so another definition for adaptation is a defense mechanism, and it could be anything like paranoia or humor. So you'll have to decide which one I'm going to use. So these are the threats that I outline for deltas today. And they're listed here. There's changes in discharge. This could be the climate effects related to climate change. It could be changes in discharge due to engineering. Dams, diversions, changes in distributary channels that are reduced, irrigation canals. But there could be also a large story behind the sediment delivery. And I think I will demonstrate later in the talk that we've been building large dams at a rate of approximately 1 per day for over 100 years. Changes in sea level have both a climate story to it and a human story. We'll hear about that. Changes in land use, very important in how deltas are today, changes in the ecosystem. And we'll mention a couple things about changes in storm intensity or frequency. So let's start with changes in discharge. I borrowed this slide from Charlie Boris-Marty of the Global Water System Project. And he writes that this is a pandemic of engineering in surface water. We humans are distorting the natural flow of water at a rate and level and intensity that's hard to imagine. We've increased the amount of water stored in the river system by 700%. Now, several years of residence time of fresh water is stored in our own reservoir basins. The transit time, the time it takes for rainfall to land on the ground surface and make its way to the coast, has changed from 20 to 60 days on average around the world. And all of this leads to changes in the aquatic biodiversity, with diatoms, for instance, growing in dam reservoirs. And you can see here that some rivers now have more discharge because of diversion. Some rivers have much less discharge due to dams. We've taken out the flood waves, but we've also changed the bottom of the low discharge levels too. And in most cases, you just see a long-term decline in the state of discharge. So, human impacts on the hydrological system are large, and they affect delta systems. Another change in discharge is flow routing. So there are many dimensions to humans impacting flow routing on deltas. I'd like to tell you just a couple stories. The first story is on the Italian river system, the Po. The Po, before the 11th century AD, used to flow into two distributary delta systems right here. Very small deltas, equilibrium with the wave climate. But the Bolognese population, they wanted to transport their goods to the Venetians. So they cut a canal to join this very small river called the Po. And so it changed from this equilibrium condition. It moved it all here, focused energy in terms of the water, but also this was the same time of high deforestation. A lot of sediment was coming here, and you had a delta growing. In 1640, the Venetians were very unhappy with their lagoon filling up with sediment. So they had this system replumbed so that it no longer would contribute turbid water to their lagoon. And so the delta itself is very human in nature. It exists there because of human activities. That's one example of flow routing changes. Another one, if you look at the old maps, and you can go back to the times of the Romans, very nice maps. This is a river system that used to have around 16 distributary channels. Now there's basically only two. There's four, but there's mostly two big ones. So we've reduced the number of distributary channels, replaced it with canals. Now there's almost only 2% of the water and almost no percent of the sediment that gets out into the coastal zone. So these delta systems are retreating rapidly. One final part of the story is this flood magnitude developed by the Dartmouth Flood Observatory that works with CSDMS. Here they map the world's floods on a daily basis, and they've been doing this for almost 20 years using satellite systems. And here from 1985 to the present is the flood magnitude, both in magnitude on greater than 4. This is the small to large, the medium to large, and this is the very large, the greater than 6. And in both cases, the size of the floods on these rivers seems to be increasing. So the question is this human? Is this human because of climate change? Is this human because of changes in how we plumb the river systems themselves with levees, stop banks, and other diversion barrages? It's a question, and it's a question that we're studying. Finally, in this changes in discharge, this is the story that's most common. We have river systems such as the Indus, and the black line is the volume of water that reaches the coast. And you can see the volume of water has been decreasing since the early 1930s. And of course, along with the water is a decrease in the sediment discharge that goes and is carried by the water. There are many reasons for this decrease in the Indus. One of them is the barrages that are put in that disperse the water into desert areas for agricultural purposes. This flow chart indicates that if you had 108 units of water going into the Gadu barrage system on the Indus, 56 of those units were getting diverted into the agricultural desert. Some of the water is getting consumed by evaporation or domestic use. Some of it's getting consumed through canal diversions into the agricultural fields, crop use. They pump water into the desert themselves for later withdrawal. There's evapotranspiration both in the soil and from plants. And then only half of that gets down the river until you get to the very part of the coast where almost nothing reaches it. This is a very common story. This is a diagram from my colleague John Milliman. And in it, the large red dots are river systems that have changed their discharge by more than 10%. In red, you will see that the discharge is decreased. In green, you'll see that it's increased. So some of this is from climate, but most of it is from human consequences. And so these consequences are many, from changes in biodiversity, reduced coastal nutrients, because you're not carrying anything anymore. You have saltwater intrusion, saline soils. You have changes in the coastal salinity. In the Indus case, you used to have a lot of water getting to the coastal ocean. Now you have no fresh water. Coastal salinity has changed. You have changes in coastal temperature, and you have complete change in the water transportation system on that river. If we can move on to sediment delivery. There have been very large, equally large, maybe even larger changes in sediment delivery than water delivery. This is a diagram from my colleague Bob Mead of the U.S. Geological Survey that's determined the flux of sediment to the Gulf of Mexico of the Mississippi River system, one of the world's largest. And the scale is down here from 0, 200 to 400 million tons per year. So this is what the river system looked like at a time when humans were just starting to deforest the landscape, and we weren't using a lot of engineering to build dams and reservoirs. This is it 1980 to 1990. We've changed the flux pattern. In some rivers that never had any contribution of sediment to speak of, these rivers now bring out a lot of sediment. And they bring out this sediment because of, in this case, mining and other activities in the hinterland. But this river system that used to deliver much sediment now delivers hardly any because of the dams and reservoirs. And of course, we have human-induced diversion, so now we have, because of human activity, 2 deltas rather than 1, or actually 3 deltas. That was a North American case. Let me give you a European case. So this is the drainage basin along the coast of Spain that drains into the Mediterranean. In green is the drainage basin, and the black lines are the tributary channel systems of these rivers. This is the Ebro Basin itself. In 1908, only 3% of this drainage basin had its water intercepted through reservoirs. In 1960, we've had an increase to 22%, and in 1990, 71% of the drainage basins were intercepted by reservoirs. In the case of the Ebro, 95%. So what is the impact on discharge? A 5 times decrease over that time in the amount of water that gets to the coastal ocean. In terms of sediment load, we have an order of magnitude change in the amount of sediment that gets to the coastal ocean. We now have coastal retreat rates that are quite high, relatively high, on a delta, up to 30 meters per year. And since 1983, over 110 million tons of sediment were delivered to the Spanish coast. On the Ebro, the delivery was to maintain a road system here. There's a salt mine, it's salt ponds, and they truck the salt. And so this keeps getting broken by wave activities, and so they bring this sand to maintain that system.